Welcome to the course of Engineering Chemistry. Today we are going to continue the unit of nanoelectronics. In today's lecture, we are going to discuss about resist materials used in electron beam lithography. In electron beam lithography, what we do is we pass electron beam on a resist material which is coated on a silicon wafer. So based on the reaction that happened on the resist material, it can be either removed or it can be stayed as it is on the resist material. So today we are going to discuss what are all the resist materials that can be used on the silicon wafer and what will happen when we pass the electron beam on the resist material, and what are all the things you need to look for when you select the resist materials. So let's start the lecture. Resist materials. So resist materials are coated on a silicon wafer surface. So this is your silicon wafer. On top of the silicon wafer surface, you put this resist material. So the first thing is you coat the resist material on wafer. Next, what we will do is we put a mask. So, and then you pass. So this is the mask which will not allow the electron beam to pass. So then we will pass the electron beam. So this is your electron beam. It is passed everywhere. So when you pass the region wherever you have the mask, it will protect the electron beam in entering. As a result, wherever it is allowed to pass, like here and here, it will make changes on the resist material. So this is what we discussed in the previous lecture during when we discussed about electron beam lithography. And now we are going to discuss what are all the materials we can use here and what will happen when we change the resist type. So the first thing when you look for a resist material is you have to look for four characteristics. So the first one is tone. So tone determines the area to be removed in the process of development. So when we say development, which means you subject that material to a developer solvent and then you will see if it is removed or not. So the tone can be a positive one, which we call positive tone resist. If this is the case, it will be removed with the developer solvent. And there is another kind of tone which is called negative tone resist. So this type of resist materials are not removed with the developer solvent. And these two materials are differentiated based on the solubility of the resist material after the impact of the electron beam. So the solubility of the resist material will vary according to the change that happened during the interaction of electron beam with the resist material. When its solubility is increased, it will be removed. If it is decreased, then it will not remove, and it will remove the places where it is not subject to the electron beam. The next step what we need to look when we select the resist is sensitivity. So sensitivity is the minimum amount of dose required to develop the resist. So the dose is nothing but number of electrons per unit area. So first one you need to look for the tone, and the second one is the sensitivity. Sensitivity, as I told, is the minimum amount of dose which is required to develop the resist. So the dose is nothing but the number of electrons per unit area which is required to develop the given resist. Then the third one is resolution. Resolution is nothing but the clearness of the resist developed. So this is nothing but the smallest distance between two patterns. So the patterns are created because of the action of electron beam, and between the patterns what is the smallest distance tells the resolution of the resist material selected. And then the final one is edge resistant. So the material, the resist material what you have chosen should provide resistance to the chemical action which we call wet etching, as well as it should provide resistance to the physical action which is nothing but dry corrosion. Dry etching. The resist materials are usually discussed based on the two things. One is the positive and the negative resistance. So this positive and negative, as I discussed before, are the tone specific thing. So a positive tone resist is a kind of resist material, and its main thing is when you expose this resist to the electron beam, what will happen is it will modify the chemical composition by chain scission reactions. So what will happen is this resist material, mostly is a polymer, will be subject to chain scission when it is exposed to electron beam. So if you think that you have like a chain like this of elements, it will cut this bonds. So this is nothing but chain scission. As a result, this bigger molecule is broken down into small molecules so that it can be removed by increasing its solubility. So this is nothing but fragmentation, which is the another term we can call for chain scission. So as a result, the molecules are broken down to small, which will increase the solubility of the exposed resist material. So as a result, this resist material, once its solubility is increased, it will dissolve in the developer solvent, and it is removed. The unexposed area are left as insoluble, and as a result what you will obtain is identical copy of the mask, which means if your mask is like this, what if this is the mask and then this is your developed resist, so this is your silicon wafer and this is developed resist. So what you will obtain is a identical copy of the mask, in this case of positive tone resist. And the second kind is negative tone resist. So negative tone resist or resist materials when exposed to electron beam, what will happen is it will make cross linking between the chains. So this is nothing but you have like two chains. What will happen when you pass this electron beam is the secondary electrons produced, it will make chain cross linking. So this links the two chain, which makes new bonds, and the solubility of the resist in the exposed part is decreased. So the solubility is decreased, as a result it is not washed away by developer solvent. Instead, the unexposed part is dissolved in the solvent. So this is exactly the reverse of the positive tone resist. So obviously what you will obtain is inverse pattern of the mask. So if we use the same mask here, so this is your mask. So this resist material is negative tone, which means what you will obtain, this is the silicon wafer. So the inverse, only here you have the resist material and the remaining part is washed away by the developer solvent. So what you will get is exactly the inverse pattern or the contrast pattern of the mask used in this process. So whenever you use negative tone resist, you will get inverse pattern on the silicon wafer surface. So what we discussed up to now is we discussed about the resist materials. The resist material is usually coated on the top of silicon wafer, and then we pass the electron beam using the mask. So wherever the mask will block the electron beam, it will not develop the resist material, and wherever it is not blocking, it will make the resist material to develop. Develop is in the case of, in other ways we can say it is nothing but making chemical changes in the exposed part. So resist characteristics are of four kinds. One is of the tone, which tells that the exposed part is need to be removed or the unexposed part is going to be removed. So that will be determined based on the tone. The second one is sensitivity, which tells how much electrons per unit area of the electron beam is required to develop the resist into a pattern. And then the next one is resolution, which tells the smallest distance between the patterns created. And the next thing what you need to look for when you select a resist material is edge resistance. So edge resistance is nothing but how your resist material is resistance towards the chemical or physical action. The chemical action is nothing but wet etching, and the physical action is nothing but dry etching. So these materials can be of positive or negative tone. When it is positive tone, when we expose the electron beam, the resist material will subject to chain scission. As a result, its solubility is increased in the developer solvent, and obviously what you get is identical copy of the developer solvent. The negative tone resist is exactly opposite of positive tone, in which when you pass the electron beam on the resist material, it makes cross-linking between the polymer chains. As a result, this polymer chain will become more and more compact, which means it will not soluble on the developer solvent. So the unexposed part of the resist material is washed away by the developer solvent, and as a result what you will obtain is inverse pattern of the mask used in this process. Next we discuss about classification of resist materials. So the resist materials are classified based on their nature, which means if it is inorganic or organic. Organic is nothing but hydrocarbons, and inorganic is rest of hydrocarbons in a periodic table. And then whenever you have inorganic resist material, you need to pass only the primary electrons. The primary electrons will make all changes on the resist material. But in the case of organic resist material, the primary electrons what we pass will make secondary electrons, and this secondary electrons will have all kind of effects on the material. So when we look at the example for inorganic, it is aluminum oxide and then aluminum fluoride and lithium fluoride along with aluminum fluoride. In the case of organic, we have arylates. Example is PMMA, and then sulfones and epoxies. So now we are going to discuss two resist materials in detail. What will happen when electron beam is passed? So the first one is resist which is epoxy resist, and its type is negative tone resist. So epoxy resist is a negative tone resist, and when you remember the negative tone resist, what will happen is it will make secondary electrons and then it will ionize the compound. And here epoxy is nothing but epoxy bond. So this is epoxide bond, which is a cyclic ether. So the cyclic ether is epoxy. So here what will happen is a small energy will break this bond and it will make O minus. Because this is a strained molecule, as a result even a small energy will make this epoxy cyclic ring to break to become O minus. So this is such a negative uh, species produced in the polymer material because of the action of secondary electron. So this already produced ion, what will make is it will combine, or it will make this epoxy ring to open. As a result, what will obtain is or CHO minus and then CH2A. So what will happen here is this bond will break and it will produce O minus. So this goes, maybe let me change the color. So this band goes on top of O minus. So as a result, it gains that negative, and then this negative will join to the CH2, I mean the carbon of the broken bond, because this will become positive, so it will obviously join with the negative. Next, this formed intermediate, what will make is it will combine with the other epoxy compounds present. So as a result, this will also open up this cyclic structure and it will make new bonds. So the same thing happened here. You have this negative attached to the CH2 positive, and then this bond is broken as negative ion. So this negative ion comes from the band. So now what will happen is new bonds are formed. As a result, the solubility of this exposed area is decreased. So this is a negative tone resist. So obviously the solubility of the material will decrease based on the exposed region and the unexposed region. So the solubility is decreased. So this is not washed away by the developer solvent, and obviously you will get inverse pattern. So the first one is negative tone resist, and the next what we are going to discuss is PMMA resist. The full form is polymethyl methacrylate. So polymethyl methacrylate. So that is PMMA, and this is a kind of positive tone resist, which means this will be washed away by the developer solvent. So you have the polymer, which is PMMA. So you have, this is the continuous chain which we call polymer. And then when we pass that, so this energy comes from the electron beam. So electron beam, when you pass, it makes secondary electrons, and as a result what will happen is it will break this bond which is near to the carbonyl group, and as a result it will generate radicals because this is homolytic cleavage. Homolytic cleavage. So as a result what you will get is you get CH2 CCH3, and then this is homolytically cleaved, which means one electron from that bond is taken away by each carbon atoms. So you have this bond broken and the electrons are taken away by both the carbon atoms. And what will happen in the next carbon is similarly homolytic cleavage happens here, and this will produce again two electrons. So here you get two electrons and here you have two electrons. So this is broken and taken away by this carbon and this carbon, and here what will happen is this electron comes here and this electron goes here. As a result what you will have is you will have a double bond. Sorry, it should be here, not here. So the double bond is produced here. So now this electron is gone because this is already present in this bond. So this is n times, and the remaining part, the carbon and the CH3 and the C double bond O and OCH3 are present in the other side. This is again n times, and what is left out is you have carbon monoxide, carbon dioxide, and then methyl group and CH3CO. So these are all the byproducts produced in this reaction. So these byproducts are easily soluble in developer solvent, and as a result the exposed part is washed away in the developer solvent. So you have PMMA resist. When you pass the electron beam, it produces secondary electrons. This secondary electron makes this homolytic cleavage of carbon-carbon bond near to the carbonyl group. As a result, you will get this radical. This radical combines with the radical of nearby carbon to produce a double bond. So it produces a double bond. This is a mistake, so leave it. And so here you have the double bond, and this electron is involved in this double bond. Then here what is left out is another group which is a radical, which is again a reactive group which will affect further polymer. So the byproducts produced here are usually soluble in the solvent, and it is washed away along with the developer solvent. So today we discussed about two resist materials. One is epoxy resist and the other one is PMMA resist, and one is negative tone resist, in which when we expose the electron beam it will make bonds, new bonds, by making cross linking. As a result you will get a inverse pattern. And in the case of polymer which is polymethyl methacrylate, which is a positive tone resist, here when you pass the electron beam it will make chain scission. As a result small molecules are produced as byproducts which are usually soluble in the developer solvent, and when you complete this process you will get a pattern which is exactly identical to the mask. So in today's lecture we have discussed about resist materials. in the electron beam lithography process. So what are all the resist materials which can be used as a resist, and how these resist materials are chosen based on their characteristics, which is basically tone, sensitivity, resolution, and etch resistance. And then we have discussed about the classification of resist material based on their nature, which is inorganic and organic resist materials. And we have discussed about two examples, one for the negative tone resist and the other for the positive tone resist. And these resist materials are subject, when they are subject to electron beam, they will make like cross linking or chain scission, and accordingly you will have developed pattern which is identical or maybe inverse pattern. Thank you.